Oh dear, right. Earlier on, let's just skip and go back to that one. Earlier on, I was trying to mount some coils on the outside so I could move them around a bit and to adjust the timing. Well, needless to say, it was a bit of a flop because I wasn't getting the connection to the flux connectivity that I really wanted. The ultimate plan was all along was really to stick some coils in here, wire them up to my loom, which is what I've done here, and also put my other coils at the back, trigger coils at the back there. As you can see, it's running at the moment, but there's good news and bad news. Right, the bad news is I'm not getting nearly as much RPM and torque as what I was expecting, and I've just stepped down to because the two coils are in series and the previous one was a single coil. I was using previously 7 volts on a single coil, on a single rotor, as in a single drum like this, right? Well, because there's 2 in here, I had to put them in series. So in series, yeah. So anyway, because of that, I'm running on at the moment. I'm running on 4S instead of 2S, which makes sense because I was previously running on 2S and now I'm running on 4S because there's 2 coils in series, which means because they use twice as much voltage. And the current is basically what I was expecting. It was 240 milliamps. If you remember the 2S, I was using 290 milliamps, so I'm actually using less current. But I'm actually getting quite a good, decent RPM as well, really, considering. But there's no load on it, you see. So I'm actually getting 2,800 RPM, and that's the waveforms on the generator side of it, without a load. The bad news is when I put the load on, which is 100 milliamps, and it's dropping like a stone, it drops to about 50 milliamps, and my RPM just drops like a stone. So yeah. The current has gone up to 310 milliamps. So it's not much higher than what it would have been at 290 than up to 310. So because the previous one was 290, this has got up to 310. But yeah, it's still work to do because my output current is at 60 milliamps. So yeah, there's still problems. Obviously the coils are not ideally situated for the maximum torque, because I was talking about that when I was messing about with the jig, the actual jig setup. I was able to get a lot more torque on it. I could feel it on my hand, but in this situation I can almost stop it with my finger. So there's something not right. There's something, yeah, the timing's not quite right. But yeah, my in the previous video, something happened to the Chinese MOSFET drive, and I don't know what happened because I wasn't overloading it, but this thing packed up on me when I was swapping over from one battery to another battery. It just died. So I decided to rig up my own driver MOSFET, which is what we're running on at the moment, which is on this breadboard. So I've hooked up my own MOSFET driver and a trimmer pot to adjust the biasing so we optimize it, which is what I've set it at really at the moment. So I've got the best latching and the minimum heat dissipation, because that's when you get the MOSFET biased correctly. So I've got a 47K basically from the output section of this transistor to this NMOS. We're syncing the current rather than sourcing it. So but if I put it in series with 6S, which is an extra 2 cells, we get a much bigger output. Now let me just take the load off, because I've got a polyfuse in here, which is that little thing down there. that is a polyfuse, and it trips at 500 milliamps. I did that for a bit of safety. I didn't want to blow anything. I didn't want to blow my MOSFET or anything. So it basically trips at 500 milliamps, and this thing is at 310 milliamps. And when I first switch over to the other batteries, it actually goes up to 600 milliamps. If it doesn't speed up fast enough, then the polyfuse trips. So we have to take the load off while it speeds up. Just take the lead out, let it speed up a bit on its own first. Let it pick up some speed, then I'll switch over to the other two cells. I think I can do it now actually, because we're at 240 milliamps now. Now when I switch over to the other two cells, you see it jumps up to 400. It trips usually at 500 milliamp, but as you can hear, it's picking up speed. It's actually fairly quiet. It's quite decent. I had some vibration issues there with one of my cores rattling, so I had to try and sort that out. I hope it doesn't start up again. But it's picking up to 4,000 RPM. It's climbing still. But 4,000 RPM without a load on, we're only at 390 milliamps, which is really not bad really, but there's not enough torque, so yeah, there's still some things to do. As you can see, it runs pretty quiet on its own without that other motor that was on it. That other motor was really noisy, but obviously if I put more power through this, it would go a lot faster and I'd draw more current. But the problem with that is the whole point is to try and get the current consumption on the input down. So another way of dealing with that really is to try and sort out the output stages so that we don't draw more current, so we can cancel some of that that drag. That's probably what I need to work on really more than anything. But we've got no load on it at all at the moment, and we're at 4,000 RPM and 390 milliamps on the input to the pulse motor circuit, which is in the base down at the bottom. You can't really see it properly because of the way the lights are, but yeah. So the coils are actually, yeah, cold. They're cool, but this MOSFET gets quite toasty actually. Yeah, that's pretty toasty. Even at 400 milliamps, so it's, yeah, imagine it's dropping quite a big voltage now, because I've when you think about it, I've got 6S across it. So if you work out the voltage, that's what the batteries probably aren't fully charged either, but they're probably running down a bit. Let me just check the temperature of these, but I'm not drawing a lot of current anyway. So, but if that's 16 volts, then 19, 20, we'll call it 24 volts. So it's probably about 24 volts. So there's 24 volts basically going across that MOSFET. So I think ideally what I need to do really is to connect the coils in parallel again, so we can run it on lower voltages instead of series. That's probably the only solution really. The drive coils, put them in parallel, then I won't have to have so much voltage across the MOSFET as well, which is dissipating heat, so it's wasting energy by dissipating heat. So we need to get the voltage down, but it's going to draw more current if I do that. It'll double the current. So instead of 400 milliamps, if I put them in parallel at the moment, it would be 800 milliamps. We're getting back to what the motor used to draw, you know. Mind you, it's a lot quieter, that's one thing. It doesn't make as much noise, but let's put the load on again. Let's see what happens on the output. Right, we shot up to 200 milliamps, but then it's dropping because the speed is dropping, and yeah, disappointing. I am very disappointed, actually. I was in the kitchen making a cup of coffee, and I thought I'm going to make myself a cup of coffee and have a noodle thing or something, because yeah, I'm just going to have a curry a curry pot noodle. I don't know why they put a frog on it, I have no idea. But anyway, I'm gonna have a little break, but we're actually pushing out 110 milliamps right now on the output side. So there's some, see, the polyfuse has just tripped. The polyfuse has just cut the power off and I've dropped down to 40 milliamps idle really. The output's dropped down to what's that? 10 milliamps? Oh, it's gone to zero now. Well, yeah, I'm not happy about this, but you can see how slow it's running because, oh, the LEDs don't show up flickering on camera for some reason. You might be seeing them oscillating a bit. But it's still running. The polyfuse has just cut the power off because it's a 500 milliamp polyfuse and yeah, it's gone down to a crawl. It's still going, but it's just running really slowly. Oh, you can see the LEDs on the camera pulsating. They're actually flickering really fast to me, but on the camera, on the phone, they seem to be pulsating, which is really weird. Yeah, they're doing series, these LEDs. The reason I put them in series is so I could have a higher voltage across them, so I wouldn't pull the voltage down too much to drive the MOSFET, that's all. Right, so it just started with my finger though, so I just let it stop. You can tell by the LEDs. So it's stopping now. Probably see over there. It runs really easily though. It does run well. So if I flicker it with my finger, I can start it up. Just with my finger. Oh, I didn't go fast enough that time. The polyfuse might still be hot anyway. Let's try again. There we go. Got it started. Polyfuse will have cooled down. So we're back up to 330 milliamps. I put it back on the 4S again because it, as I say, the polyfuse keeps tripping on the 6S when I've got 6 cells in series. Anyway, so it's disappointing. The good news is it does drive my device. That's the good news. It actually works, and I'm happy about that. I'm still going to etch this circuit board for it because I think there's nothing wrong with my circuit. All I really need to do is get these coils better tuned, you know what I mean? They need to be more accurately positioned for better torque because of I rigged this up earlier on so I could show you basically what's going on, right? This is just a diagram and I've cut this out so I can rotate it, and it makes it a lot easier for me to show you what's really going on. So right, bear with me. Right, this is one trigger coil here just sticking out, and the other trigger coil is over here, down here. Now when this arrow, where's the arrow? It's a bit floppy, you have to excuse me, it's a bit bendy on my knee. So when these magnets are basically top dead center to this coil at the bottom, right, what happens is ideally we need to fire the coil just after top dead center, right? Well, the problem is that this magnet here doesn't get to that coil to trigger the coil, doesn't get there until we're almost at the end of that particular field of magnetic flux. So where it would normally be pushing at this point here and continue to push until it got to this point here where it should turn off. Instead of getting that, what we're actually getting is this magnet is coming in, it's triggering the coil somewhere around about here, and we're already near the end of that. Well, we're in the maximum flux zone really between the push-pull, but there's another problem, because as this is rotating we need it to turn off. Let me just go back a minute. We need it to turn off about here somewhere, around about there. But look, the magnets aren't actually near the coil, so what's happening is we're getting drag. So it gets to this point, right? It gets to this point, so it's pulling back on the system, because these coils haven't actually got to that coil there to turn it off again, and it's delayed. So what happens is this comes around, triggers the coil, but we've actually been pulling back on the system for quite a bit, so we're actually creating lag instead of torque to drive it forward. That's the problem. So if let's go back again to that with the arrow pointing down, which is top dead center. So we're rotating, and ideally it should turn off by the time it gets to this middle bit over here, and our coil, I'm just going to go back a minute. Oh, this coil turns it on. It's the yellow one. It's not very yellow, it's vaguely yellow, coming around, and we're using the same pole, you see, to turn it on and off. So we're coming around, and that pole's coming around, because this other pole won't turn the coil off because it's in the other axis, it's in the other polarization. It's a negative pulse. Oh, is it a positive pulse? Anyway, I'm getting mixed up. Anyway, so this comes around, and it should be turning off about there, but yeah, our magnets are still pointing up, so there's a problem there somewhere. Or I could be getting this all wrong. It could be turning off with these magnets, which is in the middle. That's another possibility. If it's turning off with these magnets, actually I need to change the wiring to see if that's what's doing it. I could do that. So if these magnets are actually doing the turning off, then we're actually turning off halfway through the cycle, so we're losing torque. We're not getting all the way through to that point there where we want to be. So if that magnet there is doing the turning off, which it could be, it's hard to see. You can't see this stuff, it's running so bloody fast, you know, you just can't see it. You've got to try and work it out. So if that one's turning it on and this one's turning it off, see what I mean? We've only got a tiny little gap. We've only got this much torque area. We've only got this much rotation torque area. That's the problem, I think. So anyway, this is why the coils are ideally situated. I hope you can understand what I'm explaining. Right, anyway, enough of that. I'm just going to have a think about this for a few days. I like the fact that it's quiet though. I had a lot more torque on the jig because of the coils freestanding. I was able to move them around the rotor, the drum, a lot more easily. It's not as easy with this. I'll have to make another extension, I think, to go on the end. But before I do that, I just really want to see if I can. Yeah, because you see the generator coils, the actual generator coils are in the middle, and they're kind of in the way of where I would like to put some trigger coils. And somebody might say, well, why don't you just tap some of the voltage off the generator coils to fire to do some of the triggering? Well, yeah, I could do that. The only issue is that these generator coils produce a lot more voltage. We're talking about somewhere around 60 to 70 to 80 volts, and I designed this circuit really for 12 volts peak to peak. And I'm a little bit worried about destroying some of the components because of the voltage being so high. I mean, I could use drop down resistors, yeah, okay, I could use a voltage divider on the input. I might try that, I might do, but I'm going to have to think about it. because it literally uses it uses milliamps. It's not using, it's really not using much current at all to turn these transistors on. It's using a fraction of, it's just 0.7 of a volt really. So yeah, I could incorporate a divider network somewhere on this breadboard somewhere, because I've got the MOSFET configured over here. So anyway, that's all to do in the next few days. A little bit of jiggery pokery with the timing to try and sort that out. Yeah. Don't know what else to say. I mean, that's the current right now, 300 milliamps on 4S. And if you remember, when I did the estimation, I was expecting it to be about that, but we're on twice the voltage and we're on the same current, twice the voltage, because we're using two in series. Anyway, I've explained all that. I'm repeating myself now. Anyway, I'm gonna go before I just start drooling. Yeah.